We can draw some connections between our simple harmonic motion and circular motion. So let's say we have some kind of object and it's spinning around in a circle, and we'll call this our initial position, this horizontal. Okay. So at a given time, a point on the circle we can say is some angle theta from its initial position. Now, if we're talking about uniform circular motion, then it means we have a constant angular velocity, and so we can say this theta equals omega t, right? Now, for the connection between simple harmonic motion and uniform circular motion, we can consider this as the origin, and consider just the x-coordinate of our particle, or our point on the circle in uniform circular motion, which you could also think of like if you're shining light down here, where would the shadow be on a screen? Up here. It's the same thing as just thinking about the x-coordinate of this point on the circle. Well, using simple trig, we've got the radius of our circle here, and so the x-coordinate of our point on the circle is just our cosine theta. But if you consider what the shadow is doing, it's moving. This would be its furthest right point, and then it's moving along the circle, and then its furthest left point would be over here. As it goes back and forth on the screen, that's moving with an amplitude that's the same thing as this radius here. So if we consider the radius to be our amplitude, our theta to be omega t, then we get x equals a cosine omega t, which is exactly the result that we were looking at when we did our simple harmonic motion. Continuing the connection, we know that we're moving around with some angular velocity, omega, right? So and we know that our tangential velocity is related to our omega. Simple relationship is omega r. So if we consider the x component of this tangential velocity, we look at a point on the circle, the velocity is this way. We've got this as our theta. Well, if we draw in a set of imaginary axes, these two angles here are alternate interior, so this is also theta, meaning that this here is 90 minus theta. So the x component of our velocity is going to be minus our tangential velocity, which is omega r, times the cosine of 90 minus theta, which reminding us that r is a, that gives us minus a omega cosine 90 minus theta equals sine theta. That's a trigonometric identity, and as we said before, theta is omega t. So the x component of the velocity of our circular motion is a omega sine, or minus a omega sine omega t. This is also the velocity as a function of time for our simple harmonic motion. And we can see the connection. We know the velocity as a function of time is the time derivative of position. If we take a time derivative of this, the derivative of cosine is negative sine. And then by the chain rule, we take a derivative of omega t and multiply out this omega. And so we get this velocity is minus a omega sine omega t. The fact that it's a sine shows us something. It tells us that velocity is maximum at theta equals 0, also known as our equilibrium position, which we know from doing some conservation of energy stuff with springs in the past. And since the sine has a maximum of 1, we know that this maximum velocity is just a omega, or the magnitude of the maximum velocity is just a omega. Again, if we consider acceleration, when we're in uniform circular motion, our acceleration is just centripetal acceleration, which is omega squared r, and that's pointing toward the center of the circle. So when we're at some angle theta, that's pointing this way. Well, this is also theta by alternate interior. So the x component is going to be the minus the centripetal acceleration times the cosine of theta. And plugging in, omega squared is omega squared. R we call A, minus omega squared. Cosine and theta is omega t. So this is our acceleration as a function of time for our simple harmonic motion. It is the x component of the acceleration for a circular motion. It's also the acceleration for a simple harmonic motion. And this, we know that acceleration is dv by dt. And if we look at our velocity, derivative of sine is cosine. And again, our chain rule multiply means that we have derivative of omega t, which is just omega. So we get another factor of omega out here. And so this is the time derivative of our velocity. And again, as we know, we can see that this acceleration is maximum at maximum displacement, because when this theta is at theta is 0 or 180, we're going to be our furthest distance from equilibrium, and that goes along with our cosine being a maximum. Cosine of 0 is 1, cosine of 180 is negative 1, so that's going to make where cosine hits its maximum value. And because cosine's maximum value is 1, we can see that our maximum acceleration is a omega squared, or the absolute value, the magnitude, I should say. This also makes sense according to what we know about, spring motion, because springs, and really any simple harmonic motion, the definition is that there's a restorative force that's proportional to displacement. So at the maximum displacement, there's going to be the maximum force, and therefore the maximum acceleration.